There we go. All right. So welcome to this introduction to power electronics. In this set of videos, we're going to be going over um, this DC to DC Book of Knowledge by Steve Roberts. So I actually found this book recently, and they're nice because they're available for free. So they actually, this company, Recom, or however you pronounce that, they've published a set of books which do a pretty good job of covering a lot of the topics that you'll see kind of in industry, right? So these are very practical books that cover, really important concepts for industry, not necessarily semiconductor theory, which should be covered in, your coursework at school anyway. So this is a really helpful set of books, and I just kind of wanted to go through and kind of discuss some of the topics that are covered within them. And so, like I mentioned, we're going to be going over this DC to DC Book of Knowledge for summer, right over this summer 2026 session. And just because I'm kind of on a time crunch, I'm kind of planning to meet once a week. I know I had originally discussed meeting twice a week, but that I don't think that's going to be feasible. And right now the plan is to just do Mondays from 5 to 6 p.m. Unless that doesn't really work for everyone here that wants to be here. We can talk about rescheduling, but I think this seems to work for you guys at least. So we'll just run with it. And so I do have the schedule published. I need to update it to reflect that we're going to be meeting once a week, but the topics should not change. Right. So these topics mostly cover all of the chapters within the book. I might go back and add some traceability to see what chapters of the book correspond to each of these topics. But that's for a later date, right? So with that, let's go ahead and get into it. So this week we're looking at linear regulators, switching regulators, and non-isolated topologies. And for those of you that don't know me, I guess people watching at a later time, my name's RJ. I've been working in power electronics for about 3 years now. I'm currently at a little company called Cesium Astro in Colorado, but they've got offices all over the place now. We're a space company, so cool stuff. Um, all right, so linear regulators, and guys, feel free to stop me at any time if you have questions. So first off, why do we need power, right? Power needs to be regulated. We can't just have a 9-volt battery and try to apply this battery to some kind of uh, any kind of chips downstream. For example, I have this inverter, this SN74LV inverter chip by Texas Instruments. And so this has a maximum voltage rating of 6.5 volts, right? If we try to apply this 9-volt battery to this chip, the chip is just going to burn up and probably break, and we might be unusable, right? So um, we need to be able to regulate this 9-volt into something that can be applied to this chip, right? And so there are two types of these DC to DC voltage regulators, and they're kind of distinguished by how the transistor is used, right? So all these regulators have some kind of transistor inside of them. These transistors are used because we're able to then control, right? Hence regulate the voltage. Right, we're able to kind of condition the power using this transistor. So we need the ability to control things, and that's why all of these regulators have a transistor in them. And so the linear regulator will maintain a constant output voltage by varying the resistance, and it's effectively adjusting this voltage divider network. And we'll kind of see what that looks like and I think in a later slide. But the idea here is that the transistor will be operating in a linear region, whereas in a switching regulator, they'll be operating in a switching region, right? So they're going to be turned on or off, right? It's kind of like a light switch, right? If you turn it on or off, that's kind of what the transistor is doing. Whereas if you have a linear regulator, it's kind of like a volume control knob, right? You're kind of adjusting little by little tiny increments, what this transistor is able to do, right? And so here we have the picture of the linear regulator. And here you can see the transistor. They've labeled it in the book as a pass transistor. And that's mostly because the current, right, is literally going from the input to the output, right? So it's just being passed on. Um, and so this pass transistor, like I mentioned, allows current to flow from the input and it's charging the output, right? And so whenever we have voltage, there's some amount of capacitance here that's actually holding the voltage up. And so by turning on this transistor, we're effectively charging up a little capacitor here to increase the voltage, right, to some certain point. And of course, if you recall, how capacitors work in general, the most voltage that can be seen at the output will be the voltage that's being applied. And if we assume that this is a perfect little switch here, then the maximum voltage that the output will see will be the input voltage. Right? And so in that sense, these linear regulators can really only step the input voltage down. Right? So if I have like a 2-volt battery, but I need to increase that voltage, the linear regulator is not going to do that. You're going to need to use some other um, power regulator. In that case, voltage regulator. In that case, it'll be some kind of switching regulator, not a linear. Um, and so how this works is there's a feedback network, right? So here we have a voltage divider, right, made of these two resistors, and we're tapping off of the voltage divider and feeding into an op amp. And this op amp is comparing the output voltage, right, being scaled down to some internal reference voltage, right? And depending on the difference of that reference voltage and the output voltage, it will send a signal to the pass transistor to send some amount of current to the output, right? And so you can imagine if this output voltage scaled down by this divider network is equal to the reference voltage, then we have Vref minus, effectively Vref, right? So this is going to be at 0, and we'll be turning off the pass transistor, right? And kind of cutting off the current from flowing to the output, right? Because the output will then be sufficiently charged and we no longer need to increase the voltage anymore. And so that's kind of how this linear regulator works, right? And here we have an example of a linear regulator. This is the 7805. It's an integrated circuit, and it comes in this little package here in the middle, right? It's got 3 tabs and this is probably used for some kind of heat sinking. So you'd probably just connect that to a big ground plane or something to kind of help any kind of heat dissipation from being cooled off. Um, and this is on the right, I found this. I think this is actually linked. So if you have the slides open, I think you can actually click this and go to where I pulled that from. So this is what the silicon die looks like inside of this package, right? So one thing some people often forget is there's a whole circuit inside of these little integrated circuits, right? It's an integrated circuit. It's got a bunch of stuff going on. And so on this silicon die is this entire block diagram effectively, right? So there's some kind of voltage divider network. I won't be able to point it out on this, but there's a voltage divider network. There's an op amp. There's some reference voltage being generated, probably from this input voltage, and then there's some tab that corresponds to the output voltage, and I'm guessing there's some over temperature protection somewhere in here as well. So pretty interesting stuff, right? And you can obviously design a linear regulator with discrete parts if you really wanted to do so, right? That could be an interesting challenge. But in most cases, we're not going to be doing that, right? If I'm at a company, I want something that works and that's well documented. I don't want to be building things up from scratch if I don't have to. And this is a case where, you know, you probably don't want to do that, right? So this is what the 7805 circuit looks like, just kind of with discrete parts. So you got resistors, there's some Zener diodes, a bunch of NPN transistors, and you know, a lot of stuff going on here. And you can just buy them off the shelf for pretty cheap, right? These things run maybe upwards of $2, right? You can get one pretty cheap. So don't need to design it yourself. So the one caveat we have with linear regulators is that they're very inefficient. But like I said, they're cheap and they're relatively easy to use, right? They just come in this 3-pin little package and you can just connect it to whatever circuit you need. Um, and so there's a thing to be said about efficiency, right? We usually denote efficiency as eta. This is a Greek letter, and it's not an N. And it measures how well a power converter is performing, really. And if we know the output power and the input power, we can calculate the efficiency as the output over the input, right? And so ideally, all the power we put in should come out, right? So if this P out is equal to P in, then we get an efficiency of 1 or unity, right? So this is 100% efficient, and that's awesome. But that never happens. So, but even when the output power is 0 in this linear regulator, right? There's a bunch of other circuitry going on here, and whenever we apply some input voltage, even if the output doesn't have any kind of load attached, right? So imagine there's no current being drawn from this output pin. There still needs to be some current flowing through a lot of these other devices. And so that's usually denoted by a bias or yeah, so a bias current I sub B or a quiescent current I sub Q. All right, so this is what we call the no load current. It's basically the current needed to operate all of this other auxiliary circuitry that's not necessarily being used all the time, right? Or you know, when there's a load attached, it's just it's always being um, drawn out of that input. And so just as an example, right? So suppose we're operating the 7805 as recommended. So I've got the data sheet pulled up here. Right, so it's got a maximum input voltage of 25 volts, minimum of 7. So I've just shot for 12 volts on the input, 0.5 volts on the output, right? And we can do that because the output is rated for, where's the current? Well, so anyways, oh, okay, there it is. So the output current is rated, I forgot to box that. The output current is rated for 1.5 amps, so we can certainly draw at least half an amp and maybe an output voltage of 5 volts, right? So we're just kind of assuming the worst case of the bias current, so 8 milliamps. And if we calculate the efficiency, we find that it's 41% efficient. And so that's absolute garbage, right? This is terrible efficiency, right? That says if we're designing a converter, right, for 100 watts, then we're really only getting 41 watts out, right? And that's pretty bad if when you get to really high power. But for low power applications, this is pretty okay. So here I've just done some math to show you guys, right, how much power we're losing. And in this case, so we're inputting about a little over 6 watts of power, but then we're only outputting 2.5 watts, right? In our case where we're designing for something that should output half an amp at 5 volts. And so you can calculate the power loss. You just take the difference of the power in minus the power out, right? And that's 3.596 watts. And you can see already, right, we're losing more power than we're actually outputting, right? So this is not good. And what's even worse is, you know, when we have this power loss, it needs to go somewhere. And what's actually happening is it's burning up through these components, right? So these components inside of the regulator have some amount of resistance. And when we have current flowing through that resistance, right, P equals I times V, or I squared R, we have what's called conduction loss. And right, these things can only get these, the 7805 chip can only get so hot before it actually breaks down. And data sheets will actually tell you how these things get hot, right? And so they often have a specification for what's called the junction to ambient thermal resistance. And this tells you how hot the silicon die will get based on the power that's being dissipated and the ambient temperature. Right, so the ambient temperature is just whatever kind of environment you're designing for. Right, as an example, maybe we're designing for room temperature, right? So about 25 degrees Celsius. Well, if we have this power loss of 3.596 watts, then our junction temperature, right, the temperature of that silicon die is going to end up being 93 degrees Celsius, and that's pretty hot. But apparently, that's not hot enough to break the device, right? So the actual maximum operating junction temperature in this case for the 7805 is going to be 150 degrees Celsius, right? And we can actually, calculate how much power we can handle before we start to break it, right? And in this case, well, in any case, we just need to make sure that whatever junction temperature that we calculate is below our maximum junction temperature, right? So this TJ max, and it's not the store, right? It's the maximum junction temperature. And here we had 93 C, and so that's below 150 C, so we're good to go. And so we typically don't want to get too close to these maximum ratings, right? So this chip has a maximum rating of 150 C, but as anything, if we have a device that's operating under high stress for a long time, it's not going to last long. And so a lot of these governing bodies, such as the Navy or NASA, they have these derating guidelines that suggest what maximum um, operating conditions you should work under. And in this case, they suggest a maximum junction temperature of 110 degrees Celsius for linear microcircuits, right? So if you find this NAVSO P3641A document, which I've linked here, it's a really long document, but at the end of it, they have these tables that outline for a lot of different parts, right? Like resistors, capacitors, diodes, what kind of voltage stresses or current stresses, all these kind of different stresses that you should be operating under. And in industry, right, a lot of times we will try to design towards these derating guidelines and kind of make sure that we aren't overstressing the devices and kind of make sure that they're lasting, a decent amount of time. Right? And so once we have like a maximum junction temperature that we're designing for, we can actually go ahead and determine how much power we can actually output. And so in this case, right, with a junction maximum temperature of 110 C, ambient of 25 C, and our junction to ambient thermal resistance that was directly from the data sheet, we can find, right, this maximum power, and in this case, it's 4.47 watts. And, you can power a little fan and a LED with that, and maybe even like a little integrated circuit, right? So these are some things you can do with 4 watts, realistically. And again, so these linear regulators are okay for low power applications, but since they are very low efficiency, they will heat up a lot and likely break down if you try to pump out too much power. Um, and so there's this kind of nice article from Texas Instruments that compares the linear and switching regulators. And you can quickly see, right, for this these integrated linear regulators and discrete linear regulators that they studied, the efficiency is only 20%, whereas for this switching regulator, right, they're getting about 84%. And so that's kind of one reason we like to study switching regulators. And switching regulators are, the next topic. So let's just jump into it. So switching regulators are a little bit more complicated than linear regulators, right? Before we kind of just have this, effectively just have a little pass transistor and a voltage divider network and an op amp. It's a relatively simple concept, these linear regulators. But the switching regulators, right, these can get into very complicated control theory. And it's actually kind of an interesting problem once if you're, interested in control theory. There's a lot of papers constantly being published on different topologies and how to control them best for different scenarios of output power, but we can get into that later, right? So these switching regulators are very different than the linear regulators, and they're actually just moving discrete packets of energy, right? So before we have energy just effectively continuously going through our pass transistor, right? Hence, it's a pass transistor. We're just continuously passing stuff over um, until the output voltage reaches its set point. But in this case, right, for the switching regulators, we actually have we usually have multiple transistors, first of all, or multiple switching devices, and they're always going to be some energy storage elements. All right, and so the energy packets are going to be filtered out, and we're going to get a nice clean DC voltage out of it, right? So let's kind of take a look at what that looks like, right? So first of all, we have inductors and capacitors to help store these energy packets. And so this is kind of just some background refresher, hopefully. But inductors and capacitors don't dissipate any energy, whereas the resistors, right, in like the feedback network, for example, and the resistance of the pass transistor, so these guys are both dissipating energy, right? So they're heating up and tanking our efficiency. Um, but in this example, right, I've got a buck converter, or they've written as a buck regulator here. So there's no resistance in the path from the input to the output. There is this resistor here, which is kind of modeling a load, right? So there's some kind of current flowing through that resistor. But that's, effectively what we'd be attaching to the output, right? Maybe like a motor or an LED. It's just modeling that effectively. Right, so if we look at the path from the input to the output, there's no resistance in the series path apart from, parasitic resistance of this switch and of this inductor. And so we're using the inductor and the capacitor to store energy, right? We're sending little discrete packets of energy, we're storing it here, and it's going to be processed effectively to create a little DC output there. So switching regulators always have at least one switch node, and the voltage is going to be jumping between different states at that switch node, depending on what the switches are doing, right? So here we have a top switch and a bottom switch, and whenever a switch is turned on, it effectively creates a short. So in this case, if I'm looking at Vx and I turn on this top switch, right, then I've created a short from Vin to Vx. And so this Vx voltage will be the same as Vin, right, minus whatever small voltage drop occurs across this switch, but we'll just assume that it's ideal for now, right? So it's creating a short. And likewise, if I turn on this bottom switch, then I've created a short between Vx and ground, right? So I'm kind of, the idea is I'm taking this node and I'm attaching it to Vin or ground, depending on, this the state of these switches, these two switches here. Um, right, so we're sending these discrete energy packets. In this case, it's a square wave voltage, right? So once the top switch is turned on, we've connected Vx to 9 volts, and then if I turn it off, then if I, okay, so this, I might need to clarify this. Oh yeah, okay, never mind. So it's, if I turn the high side switch off and then I turn the low side on, then I've connected Vx to ground, right? So this becomes 0 volts. And we usually do this at a constant frequency in these switching regulators. I mean, there are some switching regulators that do operate in a changing frequency mode, but we usually do it at a fixed frequency for simple cases. But one thing to note is we never want both the high and low side switches to be on at the same time, right? Because you can imagine if I turn both of these on, then I've created a short from the input voltage all the way to ground, right? This is basically just a short. And, if I just assume that these switches have an on resistance of 1 milliohm, which is somewhat realistic, right? A lot of MOSFETs, power MOSFETs, for example, have on resistances of about 30, 40 milliohms. So 1 milliohm is somewhat realistic, but not exactly. But anyways, if we assume that both of these switches are about 1 milliohm, right? So then I've got 1 milliohm in series with 1 milliohm in the path from input voltage to ground. So I've got a total of 2 milliohms. And if I calculate the current, right, V divided by R, I take 9 divided by 2 milliohms, then I've all of a sudden got 4,500 amps pumping through these two switches. And that's going to break the switches. So we whenever we have a high side and a low side switch, we need to make sure to drive them out of phase, right? So when one is on, the other's off. And we usually want to have some amount of dead time where both of the switches are off, right? Just to kind of safeguard us from these instantaneous times where both of them are on, right? Even if it's for like a nanosecond or whatever, right? This can be dangerous, right? That's too much current. And obviously, we've created this switch node, and it's not a great DC voltage yet. Right, we're turning it on to 9 volts and off to 0 volts. So we need a way to filter out these high frequency transitions to actually make a good DC output, right? Because we're making a DC to DC converter. This is not even close to DC yet. So we use a low pass filter, right? And we put a capacitor in parallel with our output and an inductor in series. And so these will both work to slow down any high frequency changes. The capacitor will slow down the change in voltage, and the inductor will slow down the current, right? In this kind of configuration, right? And I've just got the equations for the capacitor, right? The physical equations I see is C dV by dt. And so our change in voltage over time is inversely proportional to the capacitance, right? So more capacitance means this voltage change will be slower. Likewise, for the inductor, if I look at the equation, I have got VL is given by L di by dt. So our change in current, right, is going to be given by VL over L, or otherwise, right, said in another way, the change in current through this inductor is inversely proportional to the inductance, right? So more inductance, slower current changes. And so that's what we want, right? We want to slow these two things down in order to get a nice clean DC voltage. So here I've just shown an example of stepping the capacitance at in parallel with the output here from 1 milliohm or sorry, 1 millifarad to 100 millifarad, and you can easily see, right, that the voltage is slowing down, right? It's not seeing these fast transitions anymore. It's much slower as we step the capacitance up. And likewise, the inductance slows down the change in current, right? So here I'm stepping from 1 millihenry up to 100 millihenry. And once we get to 100 millihenry, we've effectively got no change in our current, right? And that's kind of what we want. We don't want it to be changing just because the switch node voltage is changing. And so, like I said, if we have this series inductor, right, and the path from the switch node to the output and a parallel capacitor, parallel to the output, then we have this second order low pass filter, right? These things are both working to slow down the change in voltage. And if I just assume that I've got, this 1 millifarad capacitor and I just observe what happens as I change the inductance value, right? You can kind of see how much inductance we need to make a somewhat decent DC voltage, right? So this is oscillating, maybe like from 4.3 volts to 4.5 volts ish. And that's all right. That's not terrible DC. That's much better than what we had before, right? This is just jumping from 9 volts to 0 volts. It's not even close. So we've done a somewhat good job by, increasing these values of the inductance and the capacitance. And of course, if we increase the inductance and capacitance high enough, we can pretty much filter out anything, but this is, of course, not feasible, right? So if we have a 100 farad capacitor, for example, these things are 13 pounds, and yeah, this 190 by 62 by 320, right? That's ginormous, right? That's for designing power electronics, we don't want that on our little PCB. Um, but another approach that we can take to, reducing the size is,
OJ?
yeah, what's up?
Sorry, sorry to cut you off.
Oh, you're
But
good. Yeah.
a question. Um, so it's a low pass filter,
Yep.
but then I guess it meets in the middle kind of at like around that 4.5 volts in between the 0 and the 9.
Yep.
Can you maybe like explain maybe go into depth a little bit on that, explain why that is?
Yeah. Yeah. Actually, so that actually gets a little bit into more of the control theory aspect of it.
Hmm.
And what's actually going to end up happening, right, and actually you can kind of see that here, right? So that's about 4.5 volts. So this DC voltage that we see is actually going to be related to the duty cycle of the PWM, right? So if I look at my LT Spice model, and if I just look at one of these switch waveforms, um, hang on a second. That's I might have changed something here. Anyways, that's all right. So I'm switching in this example that I had here at least at a 50% duty cycle, right? So I'm on for half the time and I'm off for half the time, right?
Okay. Yeah, yeah.
And so as I put in 9 volts, right, and I'm switching right from 9 volts to 0 volts, the DC value of this is going to be 9 volts times that 50%, right?
Hmm.
And so you can actually look at the transfer function of the buck converter, which is what I was modeling in this case. And right, the output voltage is related to, oh, I'm sorry, this is terrible writing. the input voltage times the duty cycle effectively, right? And in
Okay.
this case, we see a little bit of drop just due to the resistance of the switches and of the, this little inductor here.
Hmm.
Well, I guess it's a relatively big inductor, but um, so different converter switching regulator topologies will have different transfer functions. And it just so happens that this one, right, you're seeing half the input voltage, right? And
Right.
if I were to increase this duty cycle up to 75%, I'd see 75% of nine at the output,
Okay.
at least from the DC standpoint.
All right. That makes sense. Thank you.
Yeah. All right. All right. So yeah, right, as we increase the switching frequency, this will reduce the filter size. And this has to do with our cutoff frequency. Um, so the cutoff frequency describes the point at which we've gone 3 dB down from our, unity gain value here. And so for a low pass filter, or I mean, just like in terms of voltage, or never mind. So 3 dB down, that's the half power point, right? So we've gone down half of the power, right? And again, we're using this these voltage at the switch node to transfer energy from the input to the output, right? So we have our cutoff frequency, and for this second order LC filter, it's given by 1 over 2 pi times the square root of L times C. And if we just kind of examine, the form of this, we can quickly see that L and C are both in the denominator, right? So they're inversely proportional to our cutoff frequency. And if we have smaller values, then we can get a higher cutoff frequency, right? So if I actually switch faster, then I can just use a higher cutoff frequency, right? I can kind of push this curve out further because our goal, right, at the end of the day, maybe we're all right, maybe we're like switching up here, right? Maybe that's our fundamental frequency. I'll just draw a straight line there, right? So if I actually push my switching frequency out, right? If my switching frequency is now over here, I can also push out my filter, right? I can push maybe the cutoff to be up here or something. Uh, and our original design, the one that I was kind of simulating before, so that's switching at 500 hertz. Um, and I was looking at different sources, right? Because it's not necessarily clear what kind of cutoff frequency you want for like, your output filter. There are some sources that suggest, a fifth, or I found one that said a tenth is usually good. And if we, take that tenth and run with it, then we need a cutoff at 50 hertz. And if we kind of choose a commercially available capacitor that's not ginormous, right? It's not 13 pounds. Then we can find that our inductance is 10 millihenry, right? And that's reasonable. But that's, that the 1 millifarad capacitor is still pretty big, right? So I found one that's 100 millimeters squared, right? That's, oftentimes for a 10-watt board, which is kind of what I was just, designing. Maybe we're just designing for 10 watts of power, 4 or 5 watts of power. 100 millimeters is way too big, right? So these 10-watt boards for switching regulators, they can, get down to maybe 10 square millimeters. You don't need this 1 millifarad capacitor taking up the entire board space. Um, And so typically, we take this 10 microfarad capacitor, right? And so these are, in a 1210 package, which are, almost microscopic. Um, but if we were to run with this 10 microfarad capacitor, which is more common, we would need an inductor of 1 Henry, which is also ginormous, right? So we don't really want to be switching at 500 hertz because our filter components are going to be way too big. um, especially for low power. And so this was we're just gonna try to shoot for 50 kilohertz. So I was looking around at available. So these switching regulators actually come in integrated circuits as well, just like the linear regulator. And 500 kilohertz is a typical switching frequency for a lot of them. So that's kind of where this 50 kilohertz came out of. I didn't just pull that out of nowhere. Right, so this would be a tenth of our 500 kilohertz switching frequency. And again, if we run with using this 10 microfarad capacitor, which is, in the very tiny package, then we can actually shrink down our inductance to 1 microhenry. Uh, and so in terms of physical space, this is about, 1% of that 50 hertz switching case where, our components were just way too big. And of course, one thing to worry about is the ripple, right? If we kind of look back at when we had these ginormous components, which was here, right, there's effectively no ripple there. Um, maybe like a nanovolt if I really zoomed into that waveform. Um, but maybe we don't need that, right? Maybe we can deal with like this 11 millivolts of ripple, right? So that's pretty good DC there. And so one thing to think about, as Lucas you were asking about is well, how do we control this output voltage? And we actually use, right, we send larger packets of energy, right? We're sending these packets of energy through the switch node so we can actually send more energy or less energy depending on what we need. And there's a whole chapter on this topic, so we'll get there when we get there. It's relatively complex. It kind of requires some amount of algebra and some knowledge of semiconductors, but it's nothing we can't handle here. And so that's kind of all I had to talk about here for the switching regulators. Now we can kind of talk about some of these non-isolated topologies. So first off, in order to talk about non-isolated topologies, we need to know what an isolated topology is. And so these isolated topologies will have separate current paths. And just to be clear, we're talking about topologies of switching regulators, right? We've kind of moved on from linear regulators, and we're now accepting that switching regulators are our point of interest for the rest of this class. No more linear regulators. Um, so there's a path for the input and a path for the output, right? So here I've got a closed loop at my input, and I've got a closed loop for my output, and they're isolated by this transformer. And so what we're effectively doing, and this is a flyback converter, by the way, it's one of the most popular isolated topologies. Um, and what we're effectively doing, right, is we have a switch down here, right, and we're switching it on and off, right? So we've got our switch node again, and this is creating an AC voltage effectively, right, across this transformer winding. And as we know, just straight DC voltage can't be transferred across a transformer, right? So we need to apply some kind of AC voltage, right? And of course, this comes in the form of our switching node, right? Our switch node. Um, and these isolated topologies are very useful for protecting the input. And right, so if we have a input, maybe it's like a battery or something, and maybe I accidentally short the output, right? If I accidentally short a battery, it's just going to drain the current until that battery is depleted, and then I've got a useless, voltage source. Um, in this case, if I where I have a transformer, if I short the output, right? If I short the load here, well, then it's going to try to take more current than this transformer can handle. And this transformer will saturate and it might break, but at least it will protect the source voltage, right, from breaking down or doing something worse, right? So transformers come up a lot in systems where we need that kind of protection from the input and the output for protect the input from the output. So there are, of course, then non-isolated topologies that share the current path, right? And here we have the buck converter. Um, and again, they don't have a transformer, but they do have they usually don't have transformer. There are some cases. There's actually a non-isolated version of a flyback, which we don't need to get into now, but effectively it just uses the transformer as coupled inductors, and it's not necessarily isolated. But anyways, so here, right, we've got this direct path from the input to the output, and they're both returning right through this ground node here. Um, right, so these non-isolated topologies are going to share current paths. And there are three main types of these non-isolated topologies. And so they're the buck, the boost, and the buck boost. So I got them here directly from Wikipedia. And so the buck converter is going to be stepping the voltage down, much like the linear regulator. The boost converter can actually step the voltage up. And so that can be useful if you have, for example, a really low voltage battery, but you need to power that, like a 5-volt chip or something. And then you have the buck boost, which can either step the source voltage up or down, but it inverts the polarity. And there are, of course, non-inverting types of this buck boost converter, but this is, the most basic topology that people usually study, and it happens to invert the polarity there. And I guess so that's all I had here. I did want to kind of quickly go through maybe like a little project that you guys can consider doing, right? Especially since we're only doing this in once a week instead of every twice a week. So I was just thinking maybe like looking at solar panels and kind of working with that. That's usually a good first project. Um, Actually, I'll stop the recording here at first. I think this is kind of just me spitballing. So let me stop sharing and